Hi class, welcome to day 2 of Coronachem. This is for the grade 12 class. I said that yesterday you should memorize pages 351 and 354 on chapter 9 of your textbook because it contains the chart describing all the possible permutations of geometry that you can have as a result of how the electrons are arranged around the central atom. Also, I recommend that you go through my Vesper theory playlist. Vesper is spelled VSEPR. It stands for valence, shell, electron pair, repulsions, and it pairs up with chapter 9 of your textbook. So the notes in that playlist are way better than what I'm about to give you here. What I'm doing here is simply to motivate you, to tell you that I'm still moving through the curriculum. You should be doing the same, and that I'm here to encourage you. You can ask questions, whatever you like. I'll do a couple examples on the board. You see that the board is tiny. It's like a postage stamp. So it's not exactly the best thing to be doing the examples. That's why I recommend you go to the Vesper theory playlist. I have all the notes that I normally give in class on that playlist. So yesterday I gave you homework from page 357, practice example. Got everything set up here. Don't have the best situation. I'm using a chair and a shoebox to hold the book. So on page 357, practice example was predict the HCH and the C bond angles in the following molecule called propyne. So to predict bond angles, what you have to do is look at the central atom, and based on the number of bonds to the central atom, you can make a prediction about what the bond angles are going to be. Typically, when you have two things bound to the central atom, the bond angle is going to be 180. There are exceptions, of course. If you have three things, you'll get a bond angle of 120 typically, and if you have four things, you get 109.5. Of course, there are exceptions. We're going to explore those exceptions when we delve into the details of Vesper theory. But here's what our molecule looks like, propyne. Today is March 31st, 2020, Tuesday. Just for fun, guys, if you could check in, just write your name in the comments so I know who's coming. And I would recommend that you spread the word to your classmates so we can get more than 3 people attending. It'd be nice to have the whole class show up as though we were actually in school, because then, I mean, what are we doing here? We're furthering your education, and you have to care as least as much as I do, because you're going to university next semester. So you should take this seriously. Don't get too comfortable sitting around doing nothing at home. It's your education. Anyway, this is what propyne looks like. Anybody signing in? Now, there's 5 people signed in right now. Hi, Freeman. That's what propyne looks like. It's got 3 carbons in it. We'll call this carbon 1, carbon 2, carbon 3. So carbon 1 has 4 things attached to it. So bond angle is going to be 109.5. Carbon 2 has 2 things attached to it. Bond angle, I should say not 2 bonds, but 2 things, because there's double bonds going on over there. Bond angle is going to be 180, and this one as well, carbon 3, is going to have a bond angle of 180 degrees. So you have 2 possibilities, 109.5 and 180. It looks like some people who were not in the class were logging on, but they realized they didn't want to attend the chemistry class. So if you're one of my students, tell me you're here. The next thing we're going to look at is polarity. So we'll go to page 360 of the text. And one of the things that discovering the geometry of a molecule allows you to do is to look at the vectors of the various elements involved. And as you know, when you have differences in electronegativity between the two atoms that constitute a bond, the electrons will be closer to the more electronegative atom in the bond. And that's going to create what's called a dipole, meaning there's an imbalance in the amount of time the electrons spend with one or the other atom. That creates a slight charge on the atom that has the higher electronegativity. Now, if you align all the dipoles, they can actually cancel out. So it can sometimes happen that you have a molecule with highly electronegative atoms that cause bond polarity, but because the bond polarities are opposed in opposite directions, they actually cancel each other out. So it's possible to have a molecule that is made of polar bonds, but the molecule itself is nonpolar because of symmetry. So let's look at the example on page 360 to see how that works. It says determine, on the practice exercise, determine whether the following molecules are polar or nonpolar. They talk about NF3, nitrogen trifluoride, as the first example. So before you can draw a Lewis structure, before you can draw the Vesper theory geometry, you start by drawing a Lewis structure. So you have the atoms and the number of valence electrons that are connected to each atom. You have nitrogen, you have fluorine. Nitrogen has 5 valence electrons, fluorine has 7, and there are 3 fluorine atoms. So it's 21 plus 5, or 26 electrons have to be accounted for in nitrogen trifluoride. So let's just connect them to the central atom, disperse the additional electrons that are left over to give field octets to the fluorine atom, and you have used up 18, 20, 22, 24. The remaining 2 electrons go on the central atom. So that's 26 electrons accounted for. That gives you 3 bonding pairs, 1 lone pair. That adds up to 4 domains. 4 domains means the molecule has a tetrahedral archetype, but a subtype of the tetrahedral archetype in which you have 3 bonding pairs, 1 lone pair. And this is also described on pages 351 and 354 in that table that I told you to memorize a couple days ago. That the subtype of this is called pyramidal. So what happens is the molecule looks like this. So you have the nitrogen atom as the central atom. You have 1 fluorine atom in the plane of the blackboard. You can draw the lone pair pointing straight up. There's the lone pair cloud. You have 1 fluorine atom coming forward and 1 going behind the plane of the blackboard. So the molecule looks like a tripod, and the lone pair is sticking straight up. And the geometry of it is such that the bond angles here are about 107. As you know, fluorine atoms are quite electronegative, more electronegative than nitrogen, so they each have a dipole pulling this way. So the positive side of the dipole is towards the nitrogen atom, the negative side is pointing towards the fluorine atom, and there's 3 of them. So all 3 of these dipoles are pointing downwards. So the resultant dipole, if you add all the vectors together, it resolves into a dipole pointing downwards with the positive charge close to the nitrogen atom and the negative side pointing downwards. So this molecule is polar. The next one they ask us to analyze is boron trichloride. So boron trichloride, BCl3. Let's draw the Lewis structure first. Number of valence electrons. There's boron, there's 3 chlorine atoms. So boron has 3 valence electrons because it's in group 3 of the periodic table. Chlorine has 7, and there's 3 chlorine atoms. So the number of valence electrons in this molecule is 24, 21 plus 3. Draw the boron atom as a central atom, chlorine. Now, boron does not have an octet, it has a sestet. So it's fine like that. And disperse the remaining electrons around the chlorine atom, and there's your Lewis structure. So that's 3 times 6 gives you 18, 20, 22, 24. We've used up all the electrons, so that is the correct Lewis structure. Now, when you have 3 domains and they're all bonding, that's called trigonal planar. Trigonal planar means that the molecule is flat, like a ceiling fan, with a bond angle of 120 degrees. Also, chlorine is much more electronegative than boron, so the dipoles will be pointing this way. And you'll notice they all point. So even though the bonds are polar, the molecule itself is non-polar. So boron trichloride is non-polar, even though the bonds are polar. They have dipoles due to symmetry. So symmetry causes the dipoles to cancel, the vectors cancel out. Okay, so that's on page 360 in case you want to read on your own. Again, for the latecomers. Oh, hi, Saviwe. Again, for the latecomers, if you haven't checked in yet, just throw in your name, because I look it up later and I see who's been coming to class. I'm being told by the principal that I should call all your parents to get you to attend. I'm hoping I don't have to do that because you'll come of your own free will. But if nobody shows up in the next few days, I'm gonna have to start calling parents. Hi, Rebecca. So get the news out. It makes it easier for me, because if I have to go and call 30 parents, it's a real pain. What else? We're looking at now. All right, hybridization is the next thing that the textbook talks about on page 361. Now, what happens as a result of the fact that electrons don't like to be in the same neighborhood? Now, when they did all these calculations on what happens to the electrons inside the atom, the calculations were based on the hydrogen atom, because you can't solve the equations for more complex atoms. There's just too many variables. So what they did is they started playing around with the theory, and they realized that because electrons repel each other, it makes sense for them to create orbitals by combining. So what happens is you can actually get s orbitals combining with p orbitals. They're called hybrid orbitals. They actually combine, they meld into one. And for example, when you get a carbon atom that has 4 things connected to it, what you're actually getting is 1 s orbital and 3 p orbitals combining to form 4 orbitals, but they're all hybrid orbitals, just like you were hybrids of your parents. When you combine your mom and your dad's DNA, you get children, and the children look like a mix of their parents. So in the same way, hybrid orbitals are a mix of the orbitals that they were made from. So sp3 means that 1 s orbital combined with 3 p orbitals to form 4 orbitals that are now called sp3, and they look like a mix of the spherical s orbital and the lemniscate or figure 8 shaped p orbitals. This is described on page 362, 363 of the textbook. There's a nice diagram on figure 9.19 that you can have a look at. But it boils down to this. Again, if you want the detailed notes, watch the Vesper Theory playlist, because that's where all the notes are laid out. This is just an overview. If you have an s orbital with 3 p orbitals, you're going to get 4 sp3 orbitals, and the angles between them is 109.5. If you combine an s orbital with two p orbitals, you're going to get three sp2 hybridized orbitals, and the bond angle between them is around 120. If you get one s and one p orbital, you get two sp orbitals, and their bond angle is 180 degrees. Then you can also get s plus three p's plus a d. That's going to give you four sp3d orbitals, and that's going to give you trigonal bipyramidal geometry, and you get 90 and you get 120 as the bond angles. And finally, you can combine one s, three p's, and two d's, and you get five. Sorry, you get five of these, you get six of these. sp3d2 orbitals, and that's called octahedral. The book is explaining all of that. Bond angles in octahedral is always 90, at least in the archetype. Let's look at page 366, where they ask us to do some examples using this understanding. You'll see on page 366 there's a chart where they show how all the possible geometries are created by combination of various orbitals. So you can have s, p, and d orbitals combined in various combinations to generate all the geometries that we're familiar with. On page 367, the practice example asks us to predict the geometry of the molecule. So let's do that. It says, predict the electron domain geometry and the hybridization of the central atom in sulfite, SO3 2-. Page 367. So again, before you do anything, you have to find out how many electrons you're dealing with. So let's look at the atoms and the number of valence electrons associated with each atom. Sulfur is a chalcogen, so it's got 6 valence electrons. Oxygen is also a chalcogen with 6 valence electrons, and there's 3 of them in sulfite. And finally, you have 2 extra charges due to the formal charge on the ion. So 4 times 6 is 24 plus 2 gives you 26 electrons to account for. Draw your Lewis structure, disperse your extra electrons so that you can give octets to each of the oxygen atoms. 3 times 6 is 18, 20, 22, 24. You got to have 26, so 2 more on the central atom, and there's your sulfite anion. But if you draw it this way, you're going to have a negative charge on each oxygen. And sulfur wants to have possession of 6 electrons, but only has 5 of them in this situation because 1, 2, 3 plus the 2 gives you 5. So the sulfur will have a +1 charge in this case. So you can modify this structure a little bit by sharing a lone pair, and then the structure becomes like that. You still have the minus charge on each one of these oxygen atoms, at least in the Lewis structure. What you really have is 4 bonds being shared over 3 positions. So the bond character is 4 over 3. How many domains? I forgot to draw my lone pairs. There are 4 domains here. There's 1, 2, 3, 4 areas where you have electrons. So there's 4 domains. 3 of them are bonding. And yes, double bonds counts for 1 domain. 3 of them are bonding, 1 lone pair. When you have this situation, 4 domains is the tetrahedral archetype, but when you have a 3-1, one of them is a lone pair, that's called pyramidal. So what you have is this atom has to be sp3 hybridized, because that's how you're going to get four domains to put electrons into. So let's show you what that looks like. I'll erase the calculation here to make room. So let's put the double bond O pointing straight up, and then you'll have one oxygen will be in the plane of the board. One will be coming out at you. and then you could throw the lone pair going behind. Now the bond angles here are going to be a little less than 109.5. They're going to be, because of that lone pair, it's going to be pushed down a bit. So it's going to be similar to ammonia in its bond angles, maybe even a little less, because the double bond takes actually a little bit more room. So my prediction is a bit less than 107 degrees. You'd have to look it up. I don't know the exact angle, bond angle. But if you look up the bond angles of sulfite, I predict it's less than 107. It'll probably be around 106. All right, let's try the next one. Sulfur hexafluoride. Oh, I forgot to say the hybridization. So this atom would be sp3 to create the 4 bonds, and it's a tetrahedral shape basically. And the subtype of tetrahedral is that it's pyramidal because of that lone pair. Now the next one to try is the octahedral shape that we're going to get with SF6. So let's show you how that works out. Let's make as much room as possible. So SF6 is constituted of sulfur atoms and fluorine atoms. There's 6 valence electrons in sulfur. Fluorine has 7, and there's 6 fluorine atoms. So 6 times 7 gives you 42, plus the 2 plus the 6 gives you 48 electrons that have to be accounted for in the Lewis structure for sulfur hexafluoride. So we're gonna draw the. Let's make some more room here. I don't know why I'm stepping over this box all the time. So draw your 6 fluorine atoms there and disperse your remaining electrons to give octets to each of the fluorine atoms. Okay, so that's 6 times 6 is 36, plus the 10 gives you 46. Wait a minute. 36. Oh, plus 12. Sorry, 48. Yeah, there's 6 bonds here. So 48 total. We've used up all the electrons. All of them are bonding, so 6 domains. All bonding. And if you look in your chart, that predicts an octahedral point group. Octahedral means that their hybridization is sp3d2. So if you want to draw it properly, you draw your essential atom as sulfur. You got 1 fluorine going up, you got 1 going down, 2 of them coming out at you, and 2 of them going behind the plane of the board. And the bond angle between any 2 fluorine atoms, unless of course they're on opposite sides, is 90 degrees. So the bond angle between these 2 is obviously 180, but the bond angle between any two other fluorine atoms is always 90 degrees. Okay, and that's the octahedral. By the way, I made a mistake yesterday. I had a molecule which I said was square pyramidal. It was actually square planar, and that was on page There's IF5, I think, on 354. Double check where it is. Is ICL4. Yeah, ICl4 minus is square planar. Okay, so I made a mistake yesterday when I wrote it on the video. I made a comment to correct myself, but just so in case you were watching. Um, let's try a couple more. Let's go back to page 352. There's one I don't recall doing, the selenium dichloride and carbonate. Let's try those two, and then maybe you could try some homework on your own after, because I don't think I gave you the answer key for chapter 9. So you're on your own for that, but you know, if I'll assign homework, I'll do it the next day. How are those 80 questions coming, by the way? Yeah. You should do them. SCCl2. Selenium dichloride. So, selenium is a chalcogen. It's going to have 6 electrons. Chlorine is 7. You got 2 chlorine atoms. So, is there a charge on selenium dichloride? No. So 2 times 7 is 14, plus 6 gives you 20 electrons total. You draw your central atom as selenium, and then you disperse your remaining valence electrons. See if that uses them all up. 2 times 6 is 12, 14, 16, 18, 20. So you got 2 lone pairs on the central atom. No formal charges because chlorine wants possession of 7 electrons, and it has it, so there's no charge on there. Selenium wants possession of 6 electrons, being a chalcogen, and it has 2, 4, 5, 6, so that's fine as well. And chlorine on the other side is the same thing. So there's no formal charges. That's the correct structure for Lewis, the correct Lewis structure for selenium dichloride. Now you have 4 domains, 1, 2, 3, 4. You've got 2 lone pairs and 2 bonding pairs. That's called bent. If you look at your chart you have to memorize, you're going to get a bent configuration. And basically it's a subtype of tetrahedral. So to redraw it properly, you would say draw the 2 chlorine atoms in the plane of the blackboard. 1 lone pair is coming out at you, and 1 is going behind the plane of the blackboard. And the bond angle here I predict is going to be around 104.5, like water, because those lone pairs are fat. They take up a lot of room, so it's going to push down the bonding pairs. It's going to reduce it from 109.5 to 104.5. So that's the power of VSEPR theory. It makes some pretty accurate predictions, and then when they can corroborate it with actual experimental data, and they get the same number, it's a nice feeling because it means that the theory is on the right track. Let's do carbonate next. Carbonate, -2 charge. So carbon is group 14, carbon group, 4 valence electrons. Oxygen has 6, and there's 3 oxygens, and then you have an extra 2 electrons for the charge. 3 times 6 is 18, plus 2 is 20, plus 4, 24. 24 electrons in carbonate. There you go. Now, if you draw it this way, you're going to have a negative charge on each oxygen atom. 3 times 6 is 18, 20, 22, 24. It uses up all the electrons, but the way I've drawn it, carbon does not have an octet. That's no good. And on top of that, it would have a +1 charge because it wants possession of 4 electrons. That's only got 3. So the way to remedy that is to share a lone pair. And so the carbonate anion looks like this. It's going to have some double bond character. Really what you have is 4 bonds shared over 3 positions. Okay, so there's your negative 2 charges. When you have 4 domains, sorry, you have 3 domains in this, 3 domains, and they're all bonding. So that points to a sp2 hybridized. That's trigonal planar. And it's sp2 hybrid. Bond angles are around 120. Because of the double bond here, it might be a little less. This one might be actually maybe like 121 or 122. This will be around 118. Okay, so because of that double bond, there's a little bit of downward bending of those. But because those bonds are equally shared, because of resonance, they're in fact equivalent. What you actually have is 4 bonds shared over 3 positions. So this is kind of inappropriate when you think about it, because of the constant delocalization of the electrons. And so I predict if you look up the bond angles on carbonate, they should all be equal and they should all be 120. Check out whether I'm right or wrong and tell me. All right, the next thing I want to look at is the practice example. Okay, when you have multiple bonds, sometimes you get situations where you see double bonds or even triple bonds. So for example, if you have this molecule, this carbon atom is sp2 hybridized. So it means it has combined 1 s orbital with 2 p orbitals to give 3 sp2 hybrid orbitals. But you have 4 bonds here. So what's going on? How are you getting 4 bonds on the central atom when there's only 3 orbitals that have been hybridized? Well, that second bond is actually, one of them is the sp2 hybrid, but the other one is called a pi bond. Okay, so this is a sigma bond. Sigma looks like that, sigma. Let's just write it out, sigma bond. This is a sigma bond. Okay, I think sigma looks like that. Yeah, that's right, that's a sigma bond. And that's a pi bond. What does that mean? Well, a pi bond is the result of the unhybridized orbitals just sticking out at a 90-degree angle to the sp2 orbital. So if you can envision the carbon sigma bond, that's the result of overlap of the sp2 with whatever is the oxygen's presenting bond is. But there are also some unhybridized p orbitals that are 90 degrees to each other that are unhybridized. So let's pretend this is a px orbital on both of them. They're so fat that they actually end up interacting side to side. And that's what we call a pi bond. So when you have a double bond, it's actually a sigma bond and 1 pi bond. This actually constitutes 1 bond. You have. I know it looks like 2, but it's actually 1 bond. It's like 2 halves. Let's look at it that way. If you have a triple bond, say like you do with acetylene, you'll have 1 sigma bond and 2 pi bonds. Because in this case, there are p orbitals sticking above and below, and also to the side and back, above and below. So they overlap here, and they overlap there. It makes for a very messy drawing, as you can see. But these 4 constitute 2 bonds. So the book has a much better representation of it because they're kind of hard to draw, and it should be drawn carefully to see what's going on. You'll see that on page 368 and 369. So take some time to read the book. I'm going to stop it there for today. I'd like you to read up to page 371 and read about delocalization. Delocalization is this notion that electrons are constantly on the move, and if they're close to, if there are areas where the energy levels are similar, the electrons will go jumping around from in the bonds within the molecule. When you have extensive delocalization, especially as when you have, for example, a series of single and double bonds, say, for example, if a molecule has a long chain and every second bond is a double bond, you'll get some pretty highly colored molecules. If, for example, the red in tomato is caused by a molecule called lycopene, and because it's a long chain carbon backbone with alternating single and double bonds, the electrons can skip back and forth, and that creates an energy resonance that tends to correspond to the visible light. So whenever you see any of these bright colors, red, orange, yellow, green, all the colors that we can see are typically a specific wavelength of light. And electrons can give off wavelengths of light if they're at a certain energy, and they can achieve that certain energy if they have a certain resonance of delocalization. So we're going to get into that a little bit more later, but try to read up to page 371 tonight. So your homework is this: read up to page 371 and do practice example. The practice example on 371 at the bottom of the page. Okay? And I will see you tomorrow. Actually, tomorrow I have to attend a meeting, a staff meeting. I'm going to have to go on Zoom and download the app or whatever. And so that meeting happens to be at 1 o'clock in Toronto, so I'm going to attend it here at 11, which means it's going to interfere with our class time. But I'll do the class right after that. Okay? So your class will probably end up taking place at something like 3 o'clock for you. But I'm noticing that not everyone attends online, and you end up watching it later. I'm hoping it's my students watching because I'm getting 30 and 40 views. I don't know if it's my students. I hope it is. But anyway, I hope this is helpful, guys. I'm enjoying doing it, and I know it'll help you if you do it. So we'll see you tomorrow.